So our next talk is going to expand a little bit on some of the things we heard towards the end of Peter's talk about different approaches to correctness and different approaches to, correctness and incorrectness. So we have Flavio Ascari here, and go ahead.
Okay, so this talk I'm talking about a comparison of problem logic for correctness and incorrectness, because as Peter said, we had lots of program correctness in the past. We had lots of program incorrectness logics in recent years after his seminar work on incorrectness logic. And so what we did is try to compare some of these approaches in order to give some, to sort them and to have a better idea of what can do what. And also, this is the first part of the contribution, a taxonomy, in we consider some of these program logics, we organize them and try to compare them. And then we also define sufficient incorrectness logic, that is a proof system for the backward under-approximation condition that Peter mentioned. And we designed this new proof system because we had a very precise goal in mind, that was a sound and complete proof system with the idea of a backward analysis to match the backward under-approximation idea. So just to briefly start and to fix the notation, we have Hoare logic for program correctness. I use this notation, the semantics of R, for the post condition of the program R. So Hoare logic can prove correctness, but saying that Q, the post condition, is an over-approximation of the program semantics applied to P. Dually, incorrectness logic takes the same program semantics applied to P, but takes Q as an under-approximation. And in this way, it can prove real bugs in the program, and so it can prove incorrectness properties. So, incorrectness logic gave a new perspective of program incorrectness, but as I said, there were many works on program correctness before, and there have been many works on program incorrectness after. Here there are some. I just want to, for instance, here we have the backward under-approximation that he mentioned, that has a very interesting meaning, that is an backward under-approximation type of ERQ means that any state, each and every state in P, has an execution leading to a state in Q. And this is interesting because if Q, for instance, specifies an error, this means that every state in P is a witness to an error. We don't know exactly which error in Q is reached, but for every state in P, we know that it leads to one of the errors. And the importance of this property was, for instance, also recognized by Outcome Logic, published, actually now it's last year. And so this is one of the things we studied, and they say the condition we designed the proof system for in the second part of the talk. So the first part was basically the definition of the schema, and so we have Hoare logic and incorrectness logic that are well understood as over or under approximation of the forward semantics of the program. But then we also consider the backwards, what we call the backward semantics, that is the weakest possible precondition that Peter mentioned before. And so we had here, this is the backward under-approximation, or as we call it, sufficient incorrectness logic, because that's the name we gave to our proof system. And this is the backward under-approximation condition. And lastly, we consider the backward over-approximation condition, and we understood that this condition is actually the necessary precondition proposed by Couzeau et al. In 2011 first. And the idea of the necessary precondition is that whenever P is violated, then Q cannot hold at the end of the program. This is because P is necessary for Q to hold at the end, so if it is violated, Q does not hold. And this can be used, well, in a sense, both for correctness and incorrectness, depending on how you interpret P and Q. And so, for instance, if Q is the set of states of safe states, if P is violated, you have incorrectness, because if P is violated, you are not in a safe state at the end. And so it can be used also in this way. So we define this schema, we fill the gaps, because in the original formulation it was not entirely clear that necessary conditions were defined by this backward under-approximation condition. And so we use this schema to drive a comparison of these logics. And the first thing we consider is the consequence rule, that is the ability to weaken or strengthen the pre and post condition in a logic. And we have that in the schema, the consequence rule follows the diagonal. So we have both for our logic and sufficient incorrectness logic can shrink the precondition and weaken the post. And conversely, incorrectness and necessary conditions have the same consequence rule that is the opposite. So since they have the same consequence rule, we try to compare, for instance, our logic and sufficient incorrectness logic because they seem related because of this. But it turns out that the consequence rules doesn't really give much about the similarities of the logic. So we have that for our logic and the sufficient incorrectness logic are basically not related for a general program R. And we have some relation when R is deterministic. Well, if R is deterministic, the SIL condition turns out to be total completeness. And so total completeness implies our logic, that is partial completeness. And on the converse, if R is terminating, we have that for our logic it becomes total correctness, and this implies sufficient incorrectness logic. But in general, there is no relation between sufficient incorrectness logic and our logic. And for a necessary condition and incorrectness logic, the thing is even worse, let's say, because these are the, let's say, quantified versions of the conditions for necessary condition and incorrectness logic. And as you can see, they are basically the same, but for the fact that necessary condition, the first one is that for all state in the vector semantics of sigma prime, while incorrectness doesn't exist. And these two formulas are basically not related. So if you know one of the two, you basically don't know anything about the other one. So this first result was a bit surprising, but it is already something on the comparison. So what we try to do next is to compare logics along the approximation axis. So we have the two over-approximation logics that are our logic and necessary conditions. We compare them, and we found that they are strongly related. That is, a normal logic tripole, here Q, is valid if and only if the corresponding necessary precondition tripole with negated P and Q is valid. And this is a very strong relation. So with this relation, we went on for the under-approximation side. So we compared incorrectness logic and sufficient incorrectness logic. And we were a bit surprised to find no such relation. And actually, we didn't find any relation at all between IL and SIL. They are basically, let's say, an IL tripole in general does nothing about a SIL tripole and vice versa. And this lets us to understand the fact that over and under approximation are dual theory only on the surface, but there are lots of things that break the duality. For instance, as Peter said before, the definition of the program semantics is in terms of least fixed point. In both cases, if you over or under approximate, either way, you use the least fixed point of the semantics, and this is something that breaks the symmetry. Another way to see something like this is that if you compose the forward and backward semantics in both ways, you get something that is more or less increasing, but for some, let's say, particular states. And this is clearly a symmetry because both, if the theory were completely dual, you would expect swapping the order of composition, that one is increasing and the other one is decreasing or something like that. But they are both increasing, and so this clearly gives a direction of the approximation, and so it breaks the symmetry between over and under approximation. And we also observe something similar in the context of Arlstadt interpretation, where designing under approximation domains becomes difficult exactly when you take into account the semantics of programs. And so this was the first part of the work on the comparison based on this taxonomy. And then we defined our sufficient incorrectness logic proof system that you can see here on the slide. That is a proof system for the backward under approximation condition. As I said, the motivation for this is that the backward under approximation condition is very important. As I said, it was recognized already in the paper by on outcome logic that this condition gives you an interesting condition, that is the fact that every state in the precondition reach a state in the post. And so this is a way to find actual witnesses that you can use for debugging, because every state in the pre can be taken as a starting point, and then you run the program on this point and you get to a bug. And so we consider this condition interesting. But what we couldn't find was a proof system that was complete, minimal, and based on the idea of doing a backward inference of the precondition given the post condition. So we define this proof system. There's 5 core rules that are let's say, the bare minimum to have a complete proof system. And then we define some extra additional rules that are useful and can help in doing the analysis. And as Peter said, this has some things in common with incorrectness logic. For instance, the sequential rule for sequential composition is the same, but what is more interesting are the two rules, these rules for iteration, iter0 and unroll, that basically allows us to do a finite amount of unrolling of the loop and stop, and this gives us a sound under-approximation. These rules are valid for incorrectness logic, and these rules are valid for sufficient incorrectness logic too. And so this is a point in common, for instance. But there are other differences. For instance, the iteration rule in correctness logic, the iteration rule is forward, while in sufficient incorrectness logic, the iteration rule is backward. So as I said, we took this validity condition, that is the backward under-approximation, and we proved the soundness and completeness of our proof system. And we proved completeness using only the first, let's say, 5 core rules, because these are all the rules we need for completeness. But what is more interesting is the fact that the proof system favors the backward analysis. So for instance, this is an instantiation of the atom rule for Boolean guards. And as you can see, here we have a generic Q, so any post condition possible. And what we do is that we join it with the semantics of the Boolean guard, the condition. And so we get a precondition for any given post that you have at that program point. Another example is the choice rule, where we have a single post condition Q, and from that we infer, let's say, backward 2 preconditions, P1 and P2, and then we join them to match the non-deterministic join of R1 and R2. And this is, for instance, let's say, a difference with respect to incorrectness logic, because incorrectness logic, following its more forward flavor, it starts with a single precondition and derives 2 post-conditions for the 2 branches and joins them. Another example of this can be seen in the iteration rule, where Q0 is the starting point of the iteration and is completely generic. Then from Q0 we do 1 iteration of R backward and we get Q1. From Q1 we do 1 iteration backward and get Q2, and so on. And we join them all in the complex precondition. But again, we started from the single Q0, that is any possible post-condition we care about. And lastly, one of the very important points of incorrectness logic was its ability to drop disjuncts in the analysis. And we argue that SIL can do the same thing. It can drop disjuncts with respect to the backward direction of the analysis. So this is a, let's say, weaker version of the consequence rule, where if you have a disjunct P union P prime in the precondition, you can drop P prime and only care about one of the disjuncts P. Or with the empty rule, we can just ignore completely a path through the program fragment R and ignore it, putting the empty set as the precondition. And so effectively we are dropping the path that goes through the program R. So this is the basic proof system for sufficient incorrectness logic that we considered, and it was extremely important to understand the characteristic of this proof system, and for us to let's say, to really write these things down. But of course this is not an effective proof system, because in this proof system we assume P and Q to be a set of states, we use concrete semantics, we use concrete union, and so on. And so you cannot, let's say, actually implement this proof system as it is. So what we did is to instantiate it with a formula from a logic reminiscent of separation logic. We actually took inspiration from both separation logic and incorrectness separation logic. And so we gave a proof system for separation SIL. That is, we took the idea of backward under-approximation from SIL and the ability to deal with pointers from separation logic and incorrectness separation logic. And we gave kind of an effective proof system in the sense that here we have that assertions, pre and post conditions are formulae in a logic, and you have that the rules work on this formula and transform them in a way that is well, not as abstract as using concrete sets. So we took this program fragment from the paper on incorrectness separation logic that basically models the let's say the first part. You take a reference to the buffer pointed by B. Then you do a pushback operation on the vector B, and this can, in a non-deterministic way, it can reallocate the buffer underlying the vector B. And so we took this program fragment and we compared what separation SIL can do with respect to incorrectness separation logic. So incorrectness separation logic, starting from a state where the buffer is allocated, it can prove that we are in a state where x is deallocated. So a use of x after this program can lead to an error. What we did with separation SIL was kind of the opposite. We saw that there was a use of x after this program. So we started with the precondition, post-condition, specifying that x is deallocated. And we said for the rest of the heap, we don't care about anything in the rest of the heap. So we say that the rest of the heap can be whatever. We only care that x is deallocated. Then we use the SIL proof system to do a proof that basically guided us with the proof system to find this precondition. And this precondition tells us that you start where in a state where the vector B points to a valid buffer and something else in the state that we don't really care about. And the point is that this precondition is the same as SIL, but has a stronger guarantee because it tells us not that the states where x is deallocated are reachable, but it tells us that any state satisfying this precondition, so any state where B is correctly allocated, reach one of the error state. And so this gives us an actual way to tell a programmer, okay, take one of these states, any one, and from here you can see that this state has an execution leading to the error. We are not the first proof system that is able to prove a triple like this. As I said before, outcome logic recognizes the importance of this condition, and so outcome logic is able to prove basically the same triple, but for some technicalities. The difference we found out with respect to outcome logic is the let's say how we use the proof system. So the derivation is different. They can prove the same triple, but we have a different derivation in the sense that, to our understanding, outcome logic is more forward-oriented. So you start from this precondition in a sense, and you get in the end the interesting post-condition. While, as you can see in this example, the SIL proof system does the opposite. So it starts from the post-condition and builds up the pre. So this proof is read from bottom to top. You start with this. You see that you have to apply the atom rule for this atomic command. So what you do is use consequence rule to strengthen the post-condition. So from this true, so whatever is in the heap, you extract something that allows you to apply the rule for this command. Then you apply the rule and you get another post-condition. Again, from this post-condition, you want an allocation. After an allocation of y is allocated. So you extract this allocation from the true, and then you apply the rule for alloc, and you get this precondition, and so on, going all the way to the top and getting that precondition. This is not the full proof, of course. This is just a subset of just a part of the proof, but it's an interesting part because it really shows how the proof process goes from the error post condition and gets up to the interesting precondition. And so this is, like, as I said, basically the idea of SIL, and this is our proof system separation SIL instantiated for separation logic. So to conclude, we found in the literature many approaches to program incorrectness. So we took some of them and we tried to sort and compare them, and we used our schema to to try to understand what are the pros and cons of every approach. And then we designed the Sufficient Incorrectness Logic proof system that is, as I said, a proof system for the backward under-approximation condition. And here there is nothing new. It was known since at least 2019. But what is new about our proof system, it is complete, minimal, and designed with the idea of backward inference in mind. So in the future, we would like to extend the schema because the 4 main cells are already taken in the schema, but there are lots of interesting logics that are, let's say, in between 2 of these cells. So for instance, outcome logic combines things from Hoare logic and the Sufficient Incorrectness Logic, and not only that. And
there's an issue with the mic. Can you stay near this and speak in the mic?
Oh, sorry. So we have these. We have, for instance, exact separation logic. That is a combination of Hoare logic and incorrectness logic, instantiated for the separation logic setting. And we have Unter, that is the proof system that Peter mentioned before, that combines things from IL and SIL that was implemented in Pulse, and many other, and some others. And lastly, we plan on combining IL and SIL, but in a different fashion than what Unter does, and that is what Peter mentioned before, that is kind of a forward analysis with IL, followed by a backward analysis with SIL, with some interplay between them also, let's say, in the middle of the analysis. So this was everything I wanted to talk about. Thank you for the attention.
All right.
Okay, so on your previous slide, there is a word missing, very important, because you say the first complete backward, which is not true. WP is also backward, so you have to say backward under approximation.
Sorry, yeah, you're right.
And so my question is, if I take a transition system instead of the language, then I think if you take EL for the transition system, you can take SIL for the transition system, you can take EL for the inverse of the transition system, and then you will get SIL.
Yeah, this is, where is this? Okay, here. As you can see, let's say the VPP is defined exactly as the inverse relation.
It's not so clear because I don't know if you mean pre or pre-tilde, which are different.
Yeah, I mean, this is the definition for the backward semantics that we use, and this is exactly the weakest possible precondition.
Because this is true only for pre-tilde, not pre.
Yeah.
Okay, so it's pre-tilde. Okay, so I agree.
Yeah, sorry, yeah, this is a matter of, we use this notation that is maybe not entirely standard. But yeah, this is, our backward semantics is exactly given by the inverse relation of the forward semantics. If you consider the forward semantics as a relation, you take the inverse relation, and that is our backward semantics. So it's exactly the pre-tilde.
One slide you had, there was a comparison on 2 sides, and it's on the left it said, if you had there it is, yeah, deterministic on the left, you get some correspondence, not deterministic versus terminating. Those are the 2 choices.
Yep.
On the right, you said no relation, but is it true that if you had both determinism and termination on the right, then you do get a relationship? Because the quantifiers basically say the same thing.
Yeah, but the issue is that it quantifies on all states in the backward semantics. Okay. And so even if you have a deterministic program, its backward semantics may not be deterministic in the sense that many states can lead to the same output. And so when you do it backward, it's not deterministic. I think you can say something if you say that the backward semantics is deterministic or, well, terminating in a sense because you are going backward. But it's not really a condition that makes sense if you look at the program, about the program. I think the backward version of deterministic is like, if the function is injective forward, so you can go backward in just one way, but they are not really meaningful notions on the program R, because here the quantification is on the backward semantics.
Maybe it's reversible program. There's a technical definition of a reversible program. Maybe that's what you need there. Sorry.
Yeah, that may that could work. Thank you. We'll have a look into that.
Okay, I have a question.
Yeah.
So you had a paper a few years ago about how it's difficult to design abstract domains that are compatible with incorrectness logic.
Mm-hmm.
Do you know if any of those issues are like similar, or if they go away when you switch to SIL?
Yeah, that's a very interesting question. Thank you. We talk about that. We started talking about that like actually a few days ago, and we realized that those limitations actually assume, for instance, that the semantics of basic constructs is a function. And this is not true if you go backward, because if you go backward, you have many initial states that leads to the same final state. And so we started thinking about, okay, but if we go backward, we don't have those limitations anymore. And so what can we do? We can design an abstract domain, or we can like actually change our results to take into account this other thing. And no, we don't have any result yet, but it's something we thought about just a few days ago.
Hi, very nice talk. I have a question about the part about separation logic. You have a comparison from the SL, and your logic has this star true and both in pre and post condition, right?
Mm-hmm.
Is it necessary, or you can use it as a frame rule, just drop it?
Okay, so this it is kind of necessary, because you cannot specify just that X is not allocated, because if you do so, you cannot reach any state where X, because if you specify that X is deallocated, you are only talking about that part of the heap, and constraining the heap to be exactly that. And so you cannot reach a state where just X is deallocated. If X is deallocated, you end up with also having to specify that V points to something, and this something points to something else. Because you only reach states of the heap where X is allocated and these things and these other things are true. Putting here this and separately true is a convenient way to not have to talk about the rest of the heap. If you want to get rid of that, you can, but you explicitly needed to describe precisely the rest of the heap. And so in the post condition, we think it's more convenient to have this true. And once you have this true in the post condition, you get it also back in the precondition as a part of the inference process. I think you can remove it from the precondition. Like it still sound if you remove it from the precondition, basically because when you do, let's say, this process, you refine at some point you refine the true to just the part of the heap that you're interested in. So here this true refines to y points to something and separately true. If you refine it to just true, to y points to something without this and separately true, you end up without the true in the precondition. But of course, this is not something you know a priori when you do the analysis. You find out only at the end when you can remove the true in the proof.
Okay, thank you. So I understand this is necessary in your logic. So I'm curious about if you try to design the practical tool, can I always assume there's some star true in both pre and post condition, and is that sufficient to solve most of questions we're facing in the bug findings?
Sorry, can you repeat the question?
So I just want to say, if you assume that it's a star true in both pre and post condition, is there sufficient for you to build a practical tool to verify all these test cases, for example, that ISL can verify?
No, we actually only have this example. So, but I don't really think it's a big issue to have this true here, because, for instance, if you want to frame something else, you can do, because true does not conflict with it.
Okay, great, thank you.
Yeah, we'll do one more.
Professor. So thank you so much. Very nice talk. What I wanted to understand a little bit better was in this context of ISL and SIL, and you mentioned that this says a lot more than ISL because it says any state in the pre leads to somewhere in the post, right? And while in general I agree because of the interpretation of SIL, I think, or separation SIL, In this example, I'm a little confused because, okay, if you were to actually use the ISL axioms in the paper, first that existential quantification in the pre would go away. That doesn't need to be a dash, it could be an arbitrary value.
Look.
And once that's an arbitrary value, then the precondition is an exact assertion. So there's only one state in it. So even though that triple is saying everything in the post is reachable from something in the pre, there's something in the pre, there's only one thing in the pre, there's only one state that satisfies it.
Yeah.
And the whole argument that we're making in Unter and connecting it with Pulse was that if you don't arbitrarily weaken your pre using the rule of consequence, which Pulse never does, then really the kind of assertions that you get out of ISL are necessary to tell the developer what kind of problems you have.
Yeah, I mean, I agree, and no, I mean, this is indeed true. The point is that in general, here in the
But you said you only have one this example, and this is my point. I would like to see an example, but this is actually an issue. Like the practical examples that we had in ISL or we have faced in Pulse so far, we haven't actually managed to pinpoint this theoretical limitation that exists potentially on paper.
Okay, yeah, so we'll have a look into this example if it exists.
Thank you.
Great. Let's thank the speaker one more time.